While the world's attention focused on Mars happenings from a month prior, something extraordinary occurred at Venus on November 3, 2025. An ancient comet traveling through space delivered materials that shouldn't be able to exist in Venus's hostile atmosphere. What makes this remarkable is that these molecules originating from outside our solar system are actually persisting in Venus's corrosive sulfuric acid clouds. Consider how extreme Venus truly is. Soviet spacecraft melted within hours of landing there. Surface temperatures reach levels hot enough to liquefy lead. The atmospheric pressure equals being submerged a kilometer beneath Earth's oceans. The clouds consist of battery acid, yet this unforgiving world just received organic compounds, water molecules, and purified metals from a celestial wanderer that spent 10 billion years crossing interstellar space. Rather than immediate destruction, these materials are surviving, interacting and transforming Venus's atmospheric chemistry in unprecedented ways. This isn't speculative fiction. It's happening right now in November 2025. Venus's upper atmosphere is actively processing chemistry delivered from beyond our solar neighborhood just weeks ago. Cloud layers unchanged for billions of years are now circulating molecules never before part of Venus's natural chemical cycles. Unlike Mars, where deposited materials freeze on the cold surface awaiting future excavation, Venus's chemistry operates immediately, transforming, reacting, and exploring new chemical pathways in real time. The November 3rd encounter, what actually happened, the interstellar comet designated 3I Atlas, which had previously passed Mars on October 3rd, made its second close approach to an inner solar system planet. The distance measured 0.65 astronomical units, approximately 97 million kilometers from Venus. This proximity allowed Venus's gravitational field to capture material from the comet's coma, the thin envelope of vaporized gas and dust surrounding its nucleus. The distance was close enough for genuine material exchange between an interstellar visitor and a planet isolated from external chemistry for eons. The timing proves more significant than initially apparent. When 3I Atlas swept past Mars in early October, it encountered a thin atmosphere and cold, inactive surface where material simply settled and froze, essentially waiting. Venus presents dramatically different conditions. Venus possesses an atmosphere 93 times more massive than Earth's. Upper atmospheric winds reach speeds of 100 meters per second, creating superrotation that circles the entire planet in just 4 Earth days. Cloud level temperatures range from 0 to -60 degrees Celsius, cold enough for chemistry to occur, yet warm enough for reactions to proceed. Most critically, Venus harbors sulfuric acid clouds that paradoxically can preserve certain organic molecules scientists never expected to survive there. As 3I Atlas passed Venus, its coma extended millions of kilometers into space, with composition varying by distance from the nucleus. Based on the Mars encounter observations, scientists knew the comet was actively ejecting specific materials: water at rates exceeding 120 metric tons per hour, hydrogen cyanide at approximately 80 grams per second, carbon monoxide at similar rates, and unexpectedly, spectroscopic evidence suggesting unusual nickel enrichment separated from iron through uncertain natural mechanisms. Venus's gravitational field captured a fraction of these materials. Most escaped into space or deflected by solar wind, but enough remained. Estimates suggest 3 to 10% of nearby outgassing material intersected Venus's gravitational and atmospheric capture zones. The encounter geometry proved more favorable than Mars's partially glancing trajectory. Venus positioned itself closer to the outgassing stream center, meaning denser concentrations from regions nearer the nucleus arrived at Venus compared to what Mars received. Understanding Venus's layered atmospheric system to comprehend what 3I Atlas disrupted, We must understand Venus's atmospheric structure beneath simplified descriptions of hot and acidic. Venus's atmosphere isn't uniform, it's vertically stratified with distinct chemical zones, operating at different temperatures, pressures, and compositions, similar to ocean layers where surface waters differ from deeper zones. The upper cloud layer, extending from roughly 60 to 70 kilometers altitude, contains relatively dilute sulfuric acid droplets at 50–75% concentration. Temperatures here hover around 0 to -20 degrees Celsius, cold enough for water to condense into ice crystals and for certain organic molecules to remain stable longer before photochemical processes destroy them. Atmospheric pressure at this altitude is low, about 1/10 of Earth's surface pressure, meaning molecules have longer paths before colliding with others, which slows reaction rates and allows molecules to persist longer. This layer experiences most atmospheric mixing, with circulation patterns redistributing contents around the planet every 4 Earth days. The middle cloud layer, from 50 to 60 kilometers altitude, features increased sulfuric acid concentrations of 75–90% and temperatures dropping to -20 to -40 degrees Celsius. This zone produces most visible atmospheric features, the Y-shaped patterns and vortices captured by spacecraft cameras. The denser, more aggressive chemistry here means molecules surviving in the upper layer begin encountering higher acid concentrations, breaking down or transforming into different compounds. Below that, the lower cloud layer at 45 to 50 kilometers altitude reaches sulfuric acid concentrations of 80–90% with temperatures of -40 to -60 degrees Celsius. Pressure approaches 1 Earth atmosphere, creating increasingly hostile conditions for organic chemistry. This zone acts as a chemical terminus, where most surviving molecules finally break down or transform into stable end products, either incorporating into precipitation, eventually returning to the surface, or breaking into components that rise through convection to restart the cycle. By the first week of November 2025, the interstellar wanderer known as 3I Atlas had already completed its closest pass to our Sun. This momentous perihelion event occurred on October 29th, marking the point where the ancient comet came nearest to the solar furnace that had been drawing it inward for months. Following this close encounter, the comet began its long journey back toward the outer reaches of our solar system, eventually destined to return to the vast emptiness of interstellar space from which it had emerged. However, anyone assuming that this outward journey meant the comet had become dormant or inactive would be fundamentally mistaken about the nature of cometary behavior. Comets don't simply switch off their activity like a lamp being extinguished. Instead, they continue their spectacular displays of outgassing for extended periods, often weeks or even months after passing their closest point to the Sun. This prolonged activity occurs because the intense solar heating received during perihelion doesn't instantly dissipate. The comet's nucleus, composed of ancient ices and frozen materials accumulated over billions of years, continues to absorb and respond to this thermal energy even as the comet begins receding from the Sun. The sublimation process, where solid ice transforms directly into gas without passing through a liquid phase, persists as the nucleus gradually releases the heat it has absorbed. This means that even in early November, as 3I Atlas was technically departing the inner solar system, it remained a vigorously active body, ejecting massive quantities of material into the surrounding space. Water vapor constituted the primary component of this ongoing outgassing, and the quantities involved were truly staggering by any reasonable measure. Observations indicated that water was still streaming from the comet at rates hovering around 120 to 130 metric tons every single hour. To put this in perspective that makes the scale more comprehensible, this represents a slight decrease from the peak rates observed during October, when the comet was releasing more than 140 metric tons per hour. Yet describing this as a decline risks understating just how enormous these emission rates remained. Consider that a fully loaded commercial airliner typically weighs approximately 180 metric tons. This means 3i Atlas was ejecting the equivalent mass of a jumbo jet in water vapor roughly every 90 minutes, hour after hour, day after day. The vast majority of this expelled water, along with all the other materials the comet was releasing, simply escaped into the vacuum of space. The molecules dispersed outward, carried by the solar wind and the comet's own momentum, spreading into the vast emptiness that characterizes most of the solar system. This material would eventually become part of the diffuse interplanetary medium, scattered so thinly across such enormous volumes that it would be effectively undetectable. However, the situation changes dramatically when a comet passes sufficiently close to a planet, possessing both substantial gravitational influence and a significant atmosphere capable of capturing and retaining materials. Venus, the second planet from our Sun, possessed both of these crucial attributes in abundance. The planet's capture efficiency for cometary materials depended on a complex interplay of numerous physical factors, each contributing to the overall probability that molecules ejected from the comet would ultimately become part of Venus's atmospheric system. The relative velocities between the comet and the planet played a crucial role. Higher relative speeds meant materials passed through Venus's sphere of influence more quickly, reducing capture opportunities. The geometric angle of the comet's approach trajectory determined how directly the outgassing stream intersected with Venus's atmosphere. The density of the comet's coma, that extended envelope of gas and dust surrounding the solid nucleus, at the specific distance where Venus was positioned affected how much material was actually available for potential capture. Finally, Venus's atmospheric interaction cross-section, essentially the effective target area presented by its thick atmosphere, determined how much of the available material would actually encounter atmospheric molecules and be slowed sufficiently to be gravitationally bound to the planet. But scientific models incorporating all these variables suggested capture rates falling somewhere in the range between 3 and 10% for materials present in the vicinity during the critical encounter window. When these percentages are applied to the known water flux from the comet, the calculations indicate that Venus received somewhere between 3 and 12 metric tons of water distributed across the several-hour period when the comet's influence was at its strongest. In absolute terms, this quantity might seem relatively modest, especially when compared against Venus's total atmospheric water content, which is measured in many thousands of metric tons distributed throughout the planet's massive atmosphere. However, focusing solely on total quantities would miss the crucial importance of distribution patterns. This incoming water didn't arrive uniformly spread across Venus's entire globe, gently adding a homogeneous increment to the planet's water inventory. Instead, it arrived at highly specific locations determined by Venus's precise geometric configuration during those critical encounter hours. The planet's position in its orbit, its rotational state, and the exact trajectory of the comet's outgassing stream all combined to place Venus's atmosphere in the path of a relatively concentrated flow of cometary material. At these specific arrival points, local concentrations of water vapor would have been significantly, perhaps dramatically, elevated above normal background levels. This localized enhancement meant that even though the total mass of delivered water was small compared to planetary scales, the immediate chemical impact in the affected atmospheric regions could be substantial and readily detectable. Water wasn't the only significant chemical species. 3I Atlas was delivering to Venus during this encounter. Hydrogen cyanide, a molecule of profound significance for prebiotic chemistry and the emergence of organic complexity, was also streaming from the comet in remarkable quantities. Throughout October, as the comet had approached and then passed perihelion, observers had documented a truly extraordinary pattern in hydrogen cyanide production. Rather than remaining stable or showing the gradual variations typical of most cometary outgassing, HCN emissions from 3I Atlas had exhibited exponential growth, increasing dramatically as the comet drew closer to the Sun. By the time perihelion arrived on October 29th, spectroscopic measurements indicated production rates had reached approximately 75 to 100 grams per second. To appreciate just how unusual these numbers are, requires some context about typical cometary behavior. Most comets that astronomers observe and study, even during their peak activity phases, when they're most vigorously outgassing as they pass through the inner solar system, produce hydrogen cyanide at rates measured in just a few grams per second. Some particularly active comets might reach rates in the tens of grams per second under exceptional circumstances. Yet here was 3I Atlas, churning out HCN at rates that exceeded normal cometary production by 1 or even 2 orders of magnitude. This wasn't just unusual, it was essentially unprecedented in the observational record of cometary science. This extraordinary production suggested something fundamentally different about 3I Atlas's composition, or about the physical processes operating within and upon its nucleus. One likely explanation pointed to the comet's unique origin and history. Unlike comets born within our solar system, which have experienced roughly 4.6 billion years of relatively gentle conditions in the outer solar system, with occasional passes through the inner regions, 3I Atlas had formed around a different star, in a different stellar environment billions of years ago. It had then spent an almost incomprehensible span of time, perhaps 10 billion years, traveling through the near-absolute zero temperatures of interstellar space, effectively in deep freeze with virtually no external energy input. This meant that when it finally entered our solar system and began approaching the Sun, the thermal shock experienced by its nucleus was far more extreme than anything a solar system-native comet would undergo. Materials that had been locked in cold storage for eons were suddenly experiencing intense heating, driving sublimation processes that might operate very differently from the familiar patterns seen in normal comets. By November 3rd, when 3I Atlas made its close approach to Venus, the hydrogen cyanide production had stabilized somewhat, settling into a relatively steady output of approximately 80 to 85 grams per second. Over the 4 to 6 hour window when Venus's gravitational capture was most effective, and the planet's atmosphere was positioned to intercept the densest portions of the comet's coma, this production rate translated into a delivery of roughly 1.2 to 1.8 kilograms of hydrogen cyanide to Venus. While this might sound like a small quantity in absolute terms, only a kilogram or two of material, the chemical significance far exceeded what the bare numbers might suggest. Hydrogen cyanide simply isn't a normal constituent of Venus's atmospheric composition. The molecule exists there, only in negligible, barely detectable trace amounts produced through certain photochemical reaction pathways driven by solar ultraviolet radiation interacting with other atmospheric gases. Under normal, undisturbed conditions, HCN concentrations in Venus's atmosphere are so low as to be chemically insignificant for most practical purposes. The arrival of multiple kilograms of hydrogen cyanide therefore represented something genuinely novel in the truest sense, chemistry that Venus's atmospheric system hadn't encountered or been required to process in its current equilibrium state. This wasn't like receiving more of something already abundant, where the addition simply merges into the existing pool without particular consequence. This was the introduction of entirely new chemical possibilities, new reaction pathways, new potential products that weren't part of Venus's normal chemical repertoire. The chemical significance of hydrogen cyanide extends far beyond its mere presence as a molecule. In the field of astrobiology and prebiotic chemistry, HCN occupies a position of central importance as one of the key precursor molecules from which life's building blocks can be constructed. Under appropriate conditions, hydrogen cyanide readily participates in reactions that produce amino acids, the molecular units that link together to form proteins. It serves as a starting material for synthesizing nucleotides and nucleobases, the components that make up DNA and RNA, the famous Miller-Urey experiment from the 1950s, which demonstrated how organic molecules relevant to life could form from simple starting materials, prominently featured hydrogen cyanide among its products and recognized its role in subsequent synthetic pathways. When astrobiologists assess whether an environment has prebiotic potential, the capacity to generate complex organic chemistry that might eventually lead toward life, hydrogen cyanide is one of the key molecular signatures they look for. Breaking the sterility myth, organic survival in acid clouds. For multiple decades, spanning much of the modern era of planetary science, a seemingly unshakable scientific consensus dominated all discussions about Venus's potential for hosting any form of chemistry relevant to life or even complex organic molecules. This consensus held, with what appeared to be ironclad certainty backed by both theoretical considerations and experimental evidence, that Venus represented a completely sterile environment, utterly hostile to organic chemistry. The prevailing narrative maintained that anything organic, any carbon-based molecule with even remote relevance to biological systems, arriving at Venus from space would face instant, comprehensive destruction. The agents of this destruction were well understood and seemingly insurmountable: sulfuric acid clouds of formidable concentration, intense ultraviolet radiation bombarding the upper atmosphere without the protection of an ozone layer, and temperatures ranging from merely hot to absolutely infernal depending on altitude. Venus had become, in the scientific imagination and in popular understanding, the very embodiment of anti-habitability. It served as a cautionary tale, a planetary horror story illustrating what happens when conditions go catastrophically, irreversibly wrong. Scientists would point to Venus when discussing the importance of maintaining Earth's climate within habitable bounds, invoking the runaway greenhouse effect that had transformed Earth's sister planet from a possibly temperate world into a vision of hell. The message seemed clear and unambiguous. Life could never have emerged on Venus under current conditions. Complex chemistry couldn't possibly persist there for any meaningful duration, and Venus represented fundamentally dead worlds where organic chemistry went to die rather than to flourish or even simply survive. Except this understanding, despite its widespread acceptance and its foundation in genuine scientific reasoning, turns out to be not entirely accurate, or at least significantly incomplete. In March 2024, researchers published findings in the peer-reviewed journal Astrobiology that revealed something genuinely transformative about what Venus's clouds can actually support. The study took a direct experimental approach to a question that had previously been addressed primarily through theoretical arguments and assumptions. The researchers obtained samples of 20 different biogenic amino acids, not exotic or artificial molecules, but the exact same amino acids that serve as the fundamental building blocks of proteins in all Earth life, the molecules that link together in long chains to create the molecular machinery that makes biology possible. These amino acids were then subjected to conditions designed to accurately mimic the chemical environment present in Venus's cloud layers. The experimental setup used sulfuric acid solutions with concentrations matching those observed in different altitude zones of Venus's atmosphere. The temperatures were controlled to replicate the range of thermal conditions that molecules would experience as they circulated through the cloud layers. The exposure times reflected realistic estimates of how long molecules might persist in the clouds before other processes, like photochemical destruction or atmospheric circulation, carried them elsewhere. In essence, the researchers created small-scale laboratory versions of Venus's cloud environment and introduced amino acids to see what would happen to them. The hypothesis going into this experimental program, based on decades of conventional wisdom about Venus's hostility to organic chemistry, anticipated that most, or perhaps even all of these amino acids would be destroyed or at least heavily degraded by the sulfuric acid environment. This prediction followed logically from the general principle that sulfuric acid is an extremely aggressive chemical that attacks many types of molecular structures. Concentrated sulfuric acid is used in industrial chemistry precisely because of its ability to break down organic materials, to cleave chemical bonds, to oxidize and degrade molecules that resist other forms of chemical attack. Applying this general understanding to the specific case of amino acids in Venus's clouds, most scientists would have confidently predicted rapid destruction. The experimental results, however, told a dramatically and unexpectedly different story that would force a fundamental reconsideration of Venus's atmospheric chemistry. Out of the 20 amino acids subjected to Venus-like conditions, 11 demonstrated complete stability. These molecules showed no detectable reaction with the sulfuric acid, no degradation of their molecular structure, no evidence of chemical attack whatsoever. They remained intact, chemically unchanged, structurally sound, in sulfuric acid concentrations that should theoretically have destroyed them. This wasn't marginal stability or slight survival. This was comprehensive, robust persistence under conditions predicted to be immediately lethal to these molecules. But the story didn't end with those 11 completely stable amino acids. An additional 8 amino acids showed impressive stability even while undergoing some degree of chemical alteration. These molecules didn't remain absolutely unchanged, but the changes they experienced were relatively minor modifications of their structure. They transformed into chemically related compounds, derivatives that retained most of the original molecular architecture and could still be recognized as close relatives of the starting amino acids. Crucially, they didn't decompose into unrecognizable fragments, didn't break down into the simple small molecules that would indicate comprehensive destruction. The alterations were more like subtle editing than fundamental rewriting of the molecular structure. Only a single amino acid out of the entire set of 20 showed the kind of significant instability and breakdown that the original hypothesis had predicted would be universal. Just one molecule lived down to the expectations of rapid destruction in sulfuric acid. The other 19 defied those expectations in various degrees, from complete survival to recognizable transformation. This meant that 95% of the amino acids tested, 19 out of 20, either survived completely intact or survived in recognizable, chemically related forms under sulfuric acid conditions matching Venus's clouds. The implications of these findings reverberate through multiple areas of planetary science and astrobiology. These amino acids aren't exotic laboratory curiosities or specially designed molecules engineered to resist acid attack. They're the fundamental building blocks of life as we know it, the universal molecular alphabet that all Earth organisms use to construct their proteins. And they can persist in Venus's clouds. This experimental demonstration completely demolishes the long-standing assumption that Venus's sulfuric acid instantly and universally sterilizes all organic chemistry, destroying any complex carbon-based molecules unfortunate enough to find themselves in that environment. What the results reveal is that sulfuric acid's effect on organic molecules is far more selective than previously appreciated. Rather than being an indiscriminate destroyer that attacks all organic structures equally, sulfuric acid exhibits chemical preferences. It aggressively attacks certain types of molecular structures while leaving others essentially untouched or only lightly modified. The specific architecture of a molecule, the arrangement of its atoms and the types of chemical bonds holding it together, determines whether sulfuric acid will destroy it, alter it, or leave it completely alone. Some amino acids happen to possess molecular architectures that sulfuric acid simply doesn't react with under Venus cloud conditions, while others have structural features that make them more vulnerable to acid attack. This selective behavior has profound implications for understanding what happened when 3I Atlas delivered its chemical cargo to Venus on November 3rd. The amino acids that the experimental research showed can survive in sulfuric acid are precisely the types of molecules that 3I Atlas was delivering to Venus. Hydrogen cyanide, the molecule the comet was releasing in such extraordinary quantities, doesn't remain as HCN forever when it enters an environment containing water and acid. Instead, it undergoes hydrolysis reactions, chemical transformations where water molecules participate in breaking certain bonds while forming others. The products of these hydrolysis reactions include amino acids and other organic precursor molecules, exactly the kinds of compounds that the 2024 research demonstrated can persist in Venus's sulfuric acid clouds. This means that the organic chemistry arriving at Venus from the comet wasn't immediately eliminated by the acid environment. The products forming from hydrogen cyanide breakdown are now known based on direct experimental evidence rather than theoretical speculation to be stable in sulfuric acid at the temperatures characteristic of Venus's cloud layers. They don't get destroyed instantly upon arrival. Instead, they persist. They remain present in the droplets and in the atmosphere for extended periods. They remain chemically available to participate in further reactions, to serve as building blocks for more complex molecular structures, to explore the space of possible chemical configurations and potentially assemble into increasingly sophisticated compounds before photochemistry or other processes eventually break them down or carry them to regions where they can no longer survive. The nickel catalyst, accelerating unprecedented chemistry when purified nickel from the ancient interstellar comet 3I Atlas made its entry into Venus's sulfuric acid cloud layers. It didn't arrive as merely another trace element passively joining the chemical mix already present in those clouds. Nickel came bearing remarkable chemical capabilities that would fundamentally alter what kinds of chemistry Venus's atmosphere could perform. As one of nature's most effective and versatile catalysts, nickel's presence introduced capabilities that Venus's atmospheric system had never possessed throughout its entire geological history. The ability to dramatically accelerate specific chemical reactions that would otherwise proceed so slowly they'd be effectively impossible under the temperature and pressure conditions prevailing in the clouds. To understand why nickel's arrival matters so profoundly, we need to understand what catalysts actually do at the molecular level and why they're so important for determining which chemical reactions can occur in any given environment. Catalysts work through a mechanism that can be understood using a helpful analogy. Think of a chemical reaction as a journey between two valleys separated by a mountain range. The reactant molecules, the starting materials, sit in one valley at a certain energy level. The product molecules, what you get after the reaction completes, sit in another valley on the far side of the mountain. The uncatalyzed reaction requires the reactants to climb up and over the mountain to reach the product valley. This mountain represents what chemists call the activation energy barrier, the amount of energy that must be supplied to break existing chemical bonds and rearrange atoms into new configurations. For many reactions, this mountain is very high indeed, requiring so much energy that at typical temperatures, almost no molecules have enough thermal energy to make it over. The reaction proceeds incredibly slowly, so slowly that for practical purposes, we'd say it doesn't happen at all. A catalyst fundamentally changes this landscape. Rather than requiring molecules to climb over the mountain, a catalyst provides what we might think of as a tunnel through the mountain, an alternative pathway from reactants to products that requires much less energy. The catalyst achieves this by providing a surface or a molecular environment where reactants can temporarily bind in arrangements that make it easier for bonds to break and reform. The catalyst might hold two reactant molecules in close proximity and in the right orientation for reaction, or it might donate and accept electrons in ways that stabilize transition states. The crucial point is that the activation energy barrier becomes lower. The energy required to proceed along the catalyzed pathway is less than what the uncatalyzed reaction requires. This means that at any given temperature, many more molecules have sufficient energy to react via the catalyzed pathway, and the reaction proceeds much faster. Importantly, catalysts don't change the thermodynamics of a reaction. They don't make thermodynamically unfavorable reactions become favorable. If a reaction releases energy overall exothermic or absorbs energy overall endothermic, the catalyst doesn't change that fundamental energetic relationship. What catalysts change is the kinetics, how quickly a reaction reaches its thermodynamically determined equilibrium state. For reactions that are thermodynamically favorable but kinetically hindered, meaning they should occur based on energy considerations but proceed too slowly to matter, catalysts make the impossible practical, transforming reactions that would take millions of years into reactions that occur in seconds or minutes. Nickel, as a catalyst, accelerates several specific reactions that are highly relevant to Venus's atmospheric chemistry, and the most significant of these is the water-gas shift reaction. This reaction involves carbon monoxide gas and water reacting together to produce carbon dioxide and hydrogen gas. Chemically, we can write this as CO plus H2O, yielding CO2 plus H2. Venus's atmosphere now contains elevated concentrations of carbon monoxide delivered by the comet during the November 3rd encounter, and it certainly contains water, both as vapor in the atmosphere and as liquid mixed into the sulfuric acid droplets that make up the cloud layers. Under normal circumstances, without a catalyst present, these molecules could coexist indefinitely without reacting to any significant degree. The activation energy required for the water-gas shift reaction is simply too high at the temperatures prevailing in Venus's clouds. Carbon monoxide and water molecules might collide countless times without reacting because none of those collisions carries enough energy to overcome the activation barrier. But when nickel catalyst is present dissolved in the same droplets that contain water and exposed to the carbon monoxide in the surrounding atmosphere, the reaction becomes viable. Nickel provides a catalytic pathway by offering a surface or coordination environment where CO molecules and water molecules can both adsorb or bind temporarily in adjacent positions. This arrangement facilitates the electron transfers and bond rearrangements necessary for the reaction to proceed. The nickel isn't consumed in the process. It emerges unchanged from each reaction cycle, ready to catalyze the next one. A single nickel atom or nickel ion can facilitate thousands or even millions of individual reaction events over time before it eventually becomes unavailable through oxidation or incorporation into inactive chemical forms. The significance of the water-gas shift reaction proceeding in Venus's clouds becomes clear when we consider the properties and implications of the products being formed. Hydrogen gas, one of the products, is extraordinarily light, by far the lightest molecule that exists. This extreme lightness has a profound consequence. Hydrogen is the one molecular species that can actually escape from Venus's gravity entirely if it reaches sufficient altitudes in the upper atmosphere. Every other atmospheric constituent is too heavy to achieve escape velocity under Venus's thermal conditions, meaning they remain gravitationally bound to the planet indefinitely unless some very energetic process accelerates them to escape speeds. But hydrogen molecules, with their tiny mass, can be moving fast enough at typical upper atmospheric temperatures that they simply drift away into space, never to return. Hydrogen escaping from Venus represents a net loss of atmospheric mass. On the scale of individual reactions in individual droplets, this mass loss is infinitesimal, essentially unmeasurable. But if the catalyzed water-gas shift reaction proceeds extensively across billions of cloud droplets throughout the upper atmosphere for weeks or months, the cumulative effect could potentially become large enough to detect as a measurable change in Venus's overall atmospheric inventory. Beyond the escape issue, hydrogen is also remarkably reactive, despite being a stable molecule. Before hydrogen molecules reach high enough altitudes to escape, while they're still circulating through Venus's cloud layers and middle atmosphere, they can participate in reduction reactions. In reduction reactions, hydrogen acts as an electron donor, transferring electrons to other molecules and thereby altering those molecules' chemical structures. Sulfuric acid itself can be reduced by hydrogen in the presence of appropriate catalysts, producing sulfur dioxide and water through reactions that transform the highly oxidized sulfur in sulfuric acid into the lower oxidation state found in sulfur dioxide. Organic molecules can be reduced by hydrogen, gaining hydrogen atoms and altering their functional groups, their reactivity, their overall chemical behavior and properties. Nickel also catalyzes what chemists call Fischer-Tropsch type reactions, a family of chemical transformations where carbon monoxide and hydrogen combine to build longer-chain hydrocarbons or more complex organic molecules. In industrial settings on Earth, Fischer-Tropsch chemistry requires elevated temperatures, typically several hundred degrees Celsius, and increased pressures to proceed at useful rates. These industrial conditions provide the energy needed to overcome activation barriers and drive the reactions forward. However, the presence of effective catalysts, including nickel-based catalysts, dramatically lowers the temperature and pressure requirements, making the reactions viable under milder conditions than would otherwise be necessary. Venus's clouds certainly don't represent ideal conditions for Fischer-Tropsch chemistry by any conventional industrial standard. The temperatures are actually quite cold by industrial standards, and while atmospheric pressure in the cloud layers is significant, it's not the elevated pressures typically used in industrial reactors. Nevertheless, the essential ingredients are now present in Venus's clouds following the comet's delivery: nickel catalyst, carbon monoxide, and hydrogen being produced through the water-gas shift reaction. In certain droplets where concentrations happen to be elevated above average, where perhaps local atmospheric dynamics have concentrated materials, and in atmospheric regions experiencing particular temperature conditions, perhaps in zones where descending air is undergoing adiabatic compression and heating, the Fischer-Tropsch reaction pathway might proceed at measurable rates. Despite the overall conditions being far from ideal, the products would be longer-chain organic molecules, compounds more structurally complex than the simple precursors delivered by the comet, molecules that wouldn't form through simple photochemistry or uncatalyzed thermal reactions. How Venus processes its cosmic gift. The materials 3I Atlas delivered arrive directly into an active, churning atmosphere. No cold surface to archive them, no stable ice to preserve them. Chemistry began immediately. Hydrogen cyanide started hydrolyzing into ammonia and formic acid within hours. Water mixed with sulfuric acid and changed cloud droplet composition. Nickel dissolved into acid solutions and acquired catalytic roles. Atmospheric circulation distributed everything globally within days. Photochemistry began breaking down novel molecules within days to weeks. Venus operates as an alchemist, taking whatever arrives and immediately transforming it through circulation and chemistry, producing new compounds and gradually eliminating the perturbation as reactions proceed to equilibrium or photochemical destruction. The timescales are radically different from Mars, where interaction is measured in years. Materials deposited in October 2025 will remain largely unchanged until robotic excavation begins in mid-2027, roughly 20 months of waiting. Venus's interaction is measured in weeks to months. Chemistry is active now. Transformations are ongoing. By January or February 2026, much of the comet-delivered chemistry will have been photodissociated or circulated to background concentrations. The perturbation will fade naturally without external intervention. The mechanisms differ. Fundamentally, Mars involves technology, interesting interactions requiring robotic systems to excavate and heat materials. Absent human technology, Mars simply stores the comet's delivery indefinitely. Venus requires no technology. Atmospheric circulation, cloud chemistry, and photochemistry are all natural processes operating continuously. Venus explores the comet's chemistry through purely natural mechanisms. No robots needed, no excavation, no industrial heating, just planetary-scale atmospheric dynamics operating with new ingredients. What comes next? The timeline to understanding. We're standing at a specific moment in late November 2025, and everything that's happened so far is prologue. The comet encountered Venus 3 weeks ago. Materials were delivered, chemistry began, and now we're in the waiting phase where observations transition to understanding, where data becomes published findings, where speculation gives way to confirmation or refutation. Right now, ground-based observatories continue tracking 3I Atlas as it recedes from the inner solar system, still visible and outgassing, though, at declining rates. Spectroscopic measurements continue documenting water, hydrogen cyanide, carbon monoxide, and nickel emissions. These observations are critical for establishing baseline data about what the comet was producing after perihelion and how rapidly activity declined. Simultaneously, Japan's Akatsuki orbiter has completed transmitting the bulk of its Venus encounter data back to Earth. Venus orbiters have limited communication bandwidth, so downloading a complete dataset from several days of intensive observations takes weeks. By early December 2025, data should be fully received at Japan's mission control centers. Then begins the slow, methodical process of calibration and analysis, correcting raw instrument data for instrumental effects, calibrating against known standards, and processing into scientifically usable formats. January through March 2026 is when first scientific publications will appear, submitted to journals like Icarus, Geophysical Research Letters, or Nature Astronomy. Initial submissions might appear on preprint servers like Arxiv in late December 2025, allowing early community access before formal peer review completes. These papers will address specific questions. Did atmospheric composition change measurably? Were HCN or CO signatures detected? What do cloud droplet composition measurements reveal? By early 2027, the community will have consensus on broad strokes and documented disagreements on details still under investigation. This is real science unfolding in real time. The data exists, observations were made, chemistry is happening right now whether we're watching or not. Over the next 18 months, speculation gives way to confirmation, and we'll know definitively whether 3I Atlas changed Venus in the ways theory predicts. The comet arrived from beyond our solar system, carrying materials forged in another stellar environment billions of years ago. It passed through our inner solar system for a few brief weeks and delivered those materials to a planet with radically different environments. Venus is now processing that delivery through active atmospheric chemistry, teaching us about planetary systems, chemistry under extreme conditions, and how complexity can emerge when worlds receive gifts from interstellar space. The answers are coming, and when they arrive, we'll understand not just what 3I Atlas did, but what planets do when they encounter chemistry from beyond their own systems, chemistry forcing them to respond, adapt, and explore pathways never traveled before.